an exciting um, afternoon of more computer science. So, um, what we're going to talk about today is I wanted to kind of talk about the differences between shifting and rotating. And in particular, what I wanted to point out is that notice that our processor here really only has one of them. It has a rotate right command. Um, but we can actually use this to do shifting, and then also we can talk about how to rotate left. So let me open up a new file here. And then I'm going to go to our emulator. So let me just load a bit pattern into memory um, of some sort for sake of demonstration. And I'm going to take the bit pattern um, 0 followed by a 1. And then our rotate command is, the syntax for that is A is the opcode, R is the register that you store it into, and then 0 is always there, and then X is how many times to the right you rotate it. So in this case, I've loaded O1 into register 1, and I'm going to do A1, also O1, and then I'll halt. Well, actually, you know what? I'll store this out into memory. I'll just put it in FF. Um, put it out into memory. Okay, so let's run this and see what we get. Okay, so load in the bit pattern 01. We rotate. It stores it out here, and we got 80. So let's think about why we got that. If my original number is this, I got that as my, in fact, let me actually put this at the end because then it all lines up. We got that. Okay, so the rotate command does literally what I just said, namely it rotates. Okay, so if there is a bit, uh, here I rotated by one position. If there is something in the far right bit, then it kind of comes around to the far left bit. Okay. Um, okay, so that's what rotating does. Do we have any questions about this particular example? Let's start there. So you can type in the stream chat on um, Twitch or talk in Discord. I can see that too. Um, and the puppy is being ornery. She wants attention. She's not going to get it. Um, okay, so does that make sense though? We rotate it right by one position, and that's what we get. Okay, now what I want to contrast that to is shifting. Okay, if I had done a logical shift, I would have gotten this. Okay, all zeros, not. So let me actually come down here and let me put a copy of the original there so we can kind of see the difference. Okay, so what the difference is between shifting and rotating is that in a shift, a bit that falls off the far right end just falls off. In a rotate, it comes back around to the other side. Okay. All right. So does that distinction make sense first off? Okay. So maybe another way to say this with a shift is that uh, any bits that you are inserting into the left, because you have to have 8 bits, right, always get replaced with zeros. Okay, so does that make sense? The distinction here. Okay. All right, Teague, you're good. Hopefully everybody else is good too. All right, now, so here's the problem. The program that we're talking about uses the shift operator, but in assembly, the only thing that we have is the rotate. Ah, okay, Mike, very good question. We'll talk about that too. Okay, so we've got two problems. The program in question um, needs to shift both in the right and the left directions. Okay, but yet the assembly, the operations that we have, only gives us how to rotate to the right. So how do we rotate to the left is question number one. And then question number two is how do we program a shift if all we have is a rotate? Okay, and there is a way to do it. I 100% guarantee that we can do both of these things, but we need to think about them. Okay, so let's take the first question actually, which is, well, actually, let me say rotate. Okay, if I want to rotate, if I want to rotate to the left by 1 position, that's equivalent to rotating to the right by 7 positions. Okay, now how did I get 7 out of this? Yeah, exactly. 8 minus 1. And why 8? Why was 8 such an important number? Yeah, because all bit patterns on this particular machine are 8 bits. Okay, so if we were doing this on a modern processor where things are going to be 32 or 64 bits, then it would be 32 or 64 minus 1. But on our particular machine, it's an 8-bit machine, and so 8 bits, uh, the uh, so the left and the right would add up to 8. Okay, so good. That seems like you guys got that. So that actually is the easy question, right? If you want to rotate to the left by 1 position, you just rotate by 8 minus that amount to the right. Okay, so if you wanted to go 2 to the left, that's 6 to the right, 3 to the left was 5 to the right, and so on. Okay, so um, now how do you compute this? So like let's say you weren't sure how many times you need to shift. Well, uh, let's say that you need to shift 3 to the left. Well, you know the number 3 and you know the number 8, and we know how to do subtraction, right? So you could encode the number 3, encode the number 8, and then do 8 minus 3 on the computer, right? So we know how to do subtraction now. Okay, so that is the easy question. How do we do left shifting versus right shifting? Okay. Okay, and the puppy is officially getting kicked out of the office because she's bugging me. Um, okay, so that's the first question that we needed to tackle was left versus right shifting. The second one's a little bit more subtle. Um, uh, yes, okay. Mike has just uh, stumbled on something important. What if you wanted to shift to the left by 8? Then you rotate and you get the exact same bit pattern. So yes, rotating by 8 positions is equivalent to doing absolutely nothing. Um, so the answer is, Mike, you can't. You can't rotate by more than 8 positions because it looks like rotating 8 positions and 0 positions are the same thing. Another way to say that is because we're limited to 8 bits. Now, the thing with that, Mike, is that that would never happen in our algorithm. Okay, theoretically it could, but not if both numbers are 8 bits to start with. Okay, And the reason for that would be um, uh, because we were limiting ourselves to positive numbers only. The largest number that we ever could deal with is 2 to the 7th, which would involve 7 shifts, not 8. Um, so that basically is a limitation of our program. If we wanted to deal with bigger numbers, um, it is actually possible to do it, but it would be a right pain in the butt to do it, because what you would have to do is you would have to store a number. So like, let's say we had a 16-bit number. Because our machine is an 8-bit number or 8-bit processor, we would have to basically work with 8 bits at a time, and that's pretty tricky. Okay, so yes, it what's nice here is that the the sort of assumptions we made about what we were writing in our code for the project means that you never actually have to rotate by more than 7 positions, and so the problem is just sort of um, it you kind of don't have to solve it because it never happens mathematically. Okay, now shifting versus rotating was the other thing I wanted to talk about. So in our particular case for our program, this turns out not to be an issue because um, in our program, how do we, sorry, when do we shift bit patterns to the right or left? We only do the shifting if the numbers are even. Okay, and if a number is even, then what is its far right bit position? It's a 0. Okay, and so here, where the far left or far right bit position is a 1, if I rotate, then it sort of spills around into the first position. But if the far right bit were a 0 to start with, then the 0 falls off and it doesn't matter. Okay, so in our particular case, um, um, rotating and shifting are the same because we only shift in the case of even numbers. So that means that there's a 0 on the far right, and so a 0 falls off. Well, we don't have to worry about it. Okay. But let's say, for the sake of demonstration, that we didn't have that assumption. How could we take a rotate and make it into a shift? Well, what we could do is this. Um, so rotate into shift. Let me take a bit pattern, for example. Let's take this. If I rotate it, then I get that. Okay? And so, but a shift would have this. Okay, so how can I turn uh, the this first one into the second one? Well, what I could do, oops, that was not what I wanted at all. Sorry about that. Okay, so this is the bit pattern I had after I rotated. What I could do is I could say, all right, well, which bit positions do I care about? I don't care about the far left bit position because that's where some spillover happened. But I do care about the other 7. So what I could do is put a 0 in the bit position I don't care about, and a 1 in the positions I do care about, and I could AND these two guys together. Okay, so what was the trick that we used when we were trying to extract bits for the odd case, odd or even, or positive negative? We put a 1 in the position we cared about and a 0 in the positions we didn't care about. Well, here I care about everything except the far left position where the spillover may have occurred. And if I do a logical AND there, then what do I get? 5 zeros and 3 ones, which is the result of a shift. Okay, so you can always turn a you can thanks Devin. Um, um, you can always turn a rotate into a shift. It's a little harder to turn a shift into a rotate, but fortunately we don't have to worry about that. Um, yeah, exactly, Teague. Now that's for shifting right by one position. That we use the bit pattern 7F. If we were rotating by two positions, then we would actually want to use what would it be? 5F and or is it 5F? No, 3F, sorry. So this bit pattern is specific to only rotating by one position. We'd need to use different bit patterns if we were rotating by more than one position. So we rotate, and then we basically have to doctor it up by means of the carefully chosen mask. And our mask in this case is to use logical AND along with our bit pattern 7F for one bit position, and if it was more, then we would use more. Now, in the case of our program, we would never be shifting by more than one to the right at a time because we embedded that shift inside of a loop. And so if it needs to happen more than one time, well, then the loop will take care of it. But on each actual shift instruction, or rather rotate instruction, you're really only doing it one bit position at a time. Um, okay, so that turns out not to be a problem. So yeah, so let me actually go back to this file, our actual project file, and let's see why we don't have to worry about it. Okay, so so let's take our code here. So let me highlight a couple of lines there, and let's make sure that we're clear as to what they mean. Okay. So this line there, what does it mean? Uh, we only do this first while loop if um, the both numbers are even. Okay, and if they're both even, then we can basically divide out a common factor of 2 immediately, and shifting to the right is equivalent to dividing by 2, right? So that was the same thing as, like, you guys remember when we were all together in class, and I talked about working at Kohl's, and um, I had the lady after Christmas that wanted to know how much something that was 90% off was. Then, yeah. So if both numbers are even, we're going to do this procedure here, which is to uh, divide both of them by 2 and add 1 to our shift counter. If either of the numbers is odd, possibly both of them being odd, then we skip that and go directly into um, this loop. Um, yes. Okay. Um, but before we get there, let's make sure that we're clear as to what this statement means. Okay. So while condition, all right, we have a condition here that is really two smaller conditions put together, namely that. Okay. So um, num a ampersand 1 means is how in Python you tell it to do um, logical and meaning of two numbers. Okay, so the number 1 is a bit pattern, right? What is it? It's 0 followed by, or a bunch of zeros followed by a 1 in the final position. Okay, and ampersand is the logical bitwise and. Okay, which in our assembly we had been writing capital A and D. Okay, so what that's going to do is this is going to evaluate. So in the I think this is what task number, is it task number 1 to do odd versus even? I think so. Um, in task number 1 to do odd versus even, right? You have a way to figure out whether or not a number is odd or even. Okay, and so here num a ampersand 1 is just asking or saying num a ampersand 1 equals 0. Is that true or not? Is asking, is num a even or not? Okay, it either is even or it isn't. And then the second statement is doing the same thing, but for num b. Okay, so yeah, the ampersand symbol in Python is what does logical uh, bitwise anding. Okay, and this word here, and, is doing logical and in the sense of this statement could be true or false, that statement could be true or false, and it's doing the logical and of those two things. So it's kind of interesting here, excuse me, that we're using and in two different kind of senses, but each of them has a separate symbol. Ampersand is one symbol, and is another symbol, and yeah, there we go. Okay, so so this loop right here will only take place if both numbers are even. We then take okay, so Teeth's question is, what's the difference of logical and of numbers and logical and of true false? Um, let's see how to put this. In a sense, when it comes to the processor, there isn't a difference because remember, everything has to be represented by numbers anyway. Um, and let's see how to put that better. Um, oh, uh, yeah, it is kind of a difference. But there is a difference. Yeah, the difference between the symbols, right? So this is doing it bitwise in terms of numbers, and this is doing it logically. Um, the Now there is, that looks like a difference, but in terms of actual processor execution, it will end up being kind of the same thing. And maybe better put there, of course, is um, we don't have, but in our assembly, we only have one and operation. That's it. Okay. And so ultimately, both of these things will come down to the one and operation we have in assembly. But in a high level language, we can sort of, this symbol means to do one thing and this means another, and yeah, okay. We're kind of getting into the weeds there. Oh, come on, DJ Sancha and Miles. This isn't that horrible. I mean, we've been building up to this for a couple weeks, right? So, um, okay. So, this part of the code, right, only runs when, well, maybe. This part of the code only runs when both numbers are even. So if both numbers are even, you can keep popping out a factor of 2. If not both numbers are even, then it could be the case that one's even and the other's odd, or vice versa, or maybe they're both odd. In which case, like let's say that we had, for example, um, 3 and 6. Well, then I could pop a factor of 2 out of the 6, but I wouldn't add one to my shift counter. Okay? Um, and then this business here is really just the subtraction bit. And in fact, I could have actually condensed this, and instead of saying if num b less than num a, I could have just said else, like we had up here. I could have just called that else, the else case instead. Either way works. Um, yeah. So, okay. Um, now, what I wanted to talk about next was the syntax for the shift operator in Python. Okay, so the way this works is the thing before is, um, the thing before is what you're going to shift on. And the thing after is how many times you shift it. Okay. Um, and so shifting to the right by 1, well, we know how many times to shift. It's 1. Okay, now let's contrast that with this command down at the very bottom, which puts everything back together. Okay. And that's what that's going to do is take num a and shift it to the left by the number of times that have been added up in this variable shift. So the thing with the program is you don't know how many times that shift is going to happen. So let's say that it's 5 times. That you shift right 5 times up here, and so you have to shift left by 5 times down there to make up for it. Well, how do I shift left 5 times? I shift right 3 times. Okay. Maybe another way to say that is, how do I shift left once? I shift right 7 times. And I could do that procedure 5 times. So in assembly, you can, this part right there, probably the way that you guys will approach that is actually to do a loop. Okay. I claim, though, that it is possible to do it without a loop, but that takes a little bit of thought. Okay. And to kind of demonstrate the idea, let me actually come back to the program thing here. So why don't I put, let me do this. Um, and then I'll do 32 FF and C00, oops, C000. Okay, so I'm going to do something clever here. Or actually, I need to do 32. Let me do this. 3107 1 2. Um, I'll just say FF. And okay. So let me put. I've got the number 1 right here. All right. So the question is. Let me clear this back out. What's going to appear in memory cell memory cell or sorry, what's going to appear in register 2 if I run this? You might look at it and say, oh, it's going to be 1 2 FF. Okay? But I claim it's going to be something different. All right, so I'm going to step this one. So clear CPU, and I'm going to step it. All right, so notice what's here in memory cell 07. Right now it's FF. But after I run this, it's 80. Okay? And then, if I run the next instruction, it's going to load in 1280, which loads register 2 with 80, and then we halt. Okay. Um, Wait a minute. I thought it loaded register 2 with 80. Oh, sorry. I meant to do 2280. So watch this. I'm going to put FF there. Watch what happens to this memory cell. Okay, so what happened? What did my program do to memory cell 07? Okay, so memory cell 07, remember, started, I just had something there, FF, whatever. Okay, so what happened? Can you guys not hear me or something? Yeah, this is really subtle, but once you see it, you're going to be like the memes. Let's see if I can do memes on here. Okay, so um, yeah, let's blow our minds. Uh, Not quite, Mike. Okay, so Tyler, you're kind of on the right track. It changed from FF to 80, right? So why did it change from FF to 80? Well, what was happening in the program before? Okay, so let's step through it step by step. First instruction is 2101, right? Which is going to load the bit pattern 01 into the register number 1. Okay, and there it is. Next instruction is A101, which is going to rotate that by 1 position to the right. Okay, and 01 rotated by 1 position to the right is 80. Okay, what's the next instruction? 3107. What does 3107 do? Yeah, so what does the instruction 3107 do? Need the Jeopardy music here. No? We don't know what 3101 or 7 does? Not quite. Very close, Teague, but let's get your preposition straight. Nope, not quite right. Teague's a little closer, Tyler. Okay, so if we have to look back at the cheat sheet, right? The store instruction takes whatever is in a register and then puts it into a memory cell. Okay, so in this case, it's going to take whatever's in register 1, because that's that part, and sticks it into memory cell 07. Yeah. Okay. Well, what is sitting in memory cell 07 right now? Right now it's FF. Okay, but the second I execute this instruction, what is it going to be? Yeah, it'll be 80 because that's what's sitting in register 1. Okay, so there we go, right? So what I have done here is that I have actually made the program modify its own code. Okay, and this is the point where you click on the Jiffy GIF that I put up here of the sort of like dude with the head exploding. Huh? You totally can do that, Teague. Why not, right? So, I mean, why wouldn't you be able to? A program is just a sequence of numbers in memory. And one of the things that programs should be able to do is read and write from memory. Well, who says that they can't read and write from the same memory that their actual program is part of? I mean, they read from all those things, so why can't they write to it? Now, you wouldn't want to just do this willy-nilly, right? Because if you just go willy-nilly overwriting your own program, then you might just get complete garbage. Okay, but if you're very careful about it, you can make a program be self-modifying, which is exactly what I've done here. And that is the solution, or the hint maybe, for how you can tackle um, this question here, this challenge, which is try to figure out how you would do that without a looping structure. You can do it, you just have to have a self-modifying program, which is kind of clever. Um, yeah, because I'm evil. Okay, so let me go back to here. So yeah, we basically made the program self-modify. We did so very carefully though. So like I said, you don't want to employ this trick until you're really ready for it. So do not try this extra challenge until you have task 4 completely working otherwise. Then save a copy of your code and then modify the copy of it for task 4. So maybe think of the extra challenge as being like task 5 would be better put. Okay, um, because that's really quite subtle. Um, okay. Now, the other thing I wanted to talk about was, as Mike has pointed out, and maybe some of the rest of you have gotten to this point, here we have a very short program and we only ended up using, 2 or 3 registers. You've got 16 to work with, but what happens if you need more than 16 but you only have 16, right? So what happens if you need a 17th register when you don't get a 17th register? Do you just give up, or is there something else that you could do? All right, so what do you do? If you need more registers than you got, okay, you could rewrite code you don't need anymore, but you actually don't need to. Yeah, you can clear out registers you're not using anymore and reuse them for something else. Okay, that certainly would work. But if that fails, like let's say you find yourself needing 72 registers worth of stuff. Well, you don't have that, but you do have a crap ton of memory. Okay, and the programs that you guys are going to write are probably not going to take more than the first half if you will, of memory, you've got all of these other memory addresses. So, for example, um, you could use memory cells F0 all the way up through FF as another 16 temporary storage spots. Okay, so if you need more registers than you have, then you have to go back and forth to memory. Okay, yeah, so you could store something in memory, and then when you need it, load it from memory and use it, and then put the answer back into memory somewhere else. Okay, so yeah, so if you need more registers than you have, you just have to go out and use the memory. Okay, and in a sense, the memory, you can almost think of these as being like registers. They're just out in memory instead of being inside the CPU. Okay, now our processor has 16 of these registers, which is pretty luxurious if I do say so myself. Now let me contrast that to uh, let me start with another sort of ancient era processor, um, the Intel 8086. Okay, very famous processor. So when people talk about x86 processors, the 86 comes from this guy. Okay, and so this processor is on the order of performance to what was in the original Nintendo, and so what I wanted to talk about were what registers it had. Okay. Um, for general purpose stuff, so it had some specialized registers like the instruction thing and some other things. So we can ignore all of these sort of special registers. It had a program counter like we do, but in particular, its general purpose registers, it had four of them. That's it. Okay, or kind of eight in a sense, because you could take the AL register was the A low and the A high and combine them together into a register AX, which was 16 bits. So you could kind of take two 8-bit registers and put them together to be one 16-bit thing. But basically, you really only had four of these to work with: A, B, C, and D. That's it. Okay, so that's kind of limiting, right? If you've only got four registers. And so what an Intel processor would have to do is move things back and forth to memory a lot more often than we would have to on this processor. Okay. Now let's go to my other favorite processor, the MO6502, which we've talked about. Right, launched in 1975, used in the 8-bit Nintendo, and um, it's got a picture of it here. Where is the diagram? Let me find it here. Let me just blow this up. Here they are. Okay. Um, it really only had one, and then a couple of these special index ones, but it basically had one or three, depending on how you want to look at it. Um, and so, yeah, sorry about all the scrolly scroll. Um, it only had three registers basically, okay, which meant that you had to be going back and forth to memory a lot more often than you did. Okay. Now, one of the things that's really, really neat about this particular processor, though, is that so the memory that it was able to address, it was able to address a 16-bit address space. Okay, which is double the number of bits that we have for our um, in our processor. So what that meant is that so if you have 8 bits, you can address 256 cells of memory like we have here. Okay, and then if you have another 8 bits, then what that allows you to do is basically have, you could think of the memory, 16 bits worth of memory, as being 256 of these little memory. So you guys see on the screen there, there's the box that says memory, and it's a grid of 256 things. Well, imagine 256, so like print this out on paper, okay? The thing that says memory, print 256 copies of it, and stack them on top of each other like that. Okay, so down at the bottom you would have the zeroth page of memory, then the 1, then 2, then 3, all the way up to the 256th of them. Okay, and that's actually for the um, 6502, that's literally how you thought about it. Was you thought about it as being 256 pages of memory, each of which looked exactly like our memory box here on our simulator. Okay. Um, but the 6502 was kind of special in the sense that when you read or write from memory, that takes time. Okay, because memory is slower than the processor. But the way the 6502 architecture worked was that reading and writing from page 0, the one at the very bottom, was faster than reading or writing from any other page of memory. And so what that meant was that even though you only had 3 registers on board the processor, you could kind of use that very bottom, that 0th page, as a gigantic bank of registers. They were in memory, so it wasn't as fast as being on the processor, but it was better than being elsewhere in memory. Okay, which is kind of clever. Um, this processor used the first page of memory, so the 0th page is the one at the bottom. The one right after that got used for something special called the stack pointer, or the stack. We maybe will talk about that next week, but that's kind of advanced. Um, really, this is going to be uh, more relevant for anybody who's thinking of the CS major and goes on to the machine architecture class. We will talk a lot about stacks in that case. Okay, so anyway, so the long story short is if you find yourself needing more registers than you have, you're going to have to use memory. So there's really two solutions. One is either reuse registers for multiple purposes, although that can be a little tricky to keep track of. Uh, Two, try to be more efficient in your use of registers. Three would be you're going to have to use memory and load things in and out of memory as you go. Um, anyway, so okay, we should probably quit here. So let me ask if you guys have any questions. Um, and while I'm waiting for to see if you guys have any questions, um, let me show you one other thing about a real architecture. Um, Oops. Yeah, let me load a real one here. All right. So when inputting the code into the machine, do you have to use the memory cells? Well, yeah. I mean, the program's got to be in memory to start with, right? The question is just where in memory are you putting things? The program on this particular architecture must start in memory address 0, 0, right? So it has to start in the top left. That's not true of every uh, thing, but it is for many processors. Okay, so let me show you here on the 6502 processor. Oops, let me go back. Memory map, sorry. On the 6502, uh, which was used in the 8-bit Nintendo, I mentioned earlier, right, that the first 2 pages of memory were sort of special. The very bottom page you got to use as basically a giant bank of registers, and this first page you got to use basically as a for stack, which is something kind of special. Um, but then the rest of the memory, your cartridge, the memory for the cartridge, you had 8192 bytes, and that started at on page 60. Well, really 64 or whatever it is. Um, so slightly over halfway down in memory. And then in terms of your programs on the NES, your first instruction had to basically start in memory cell 8000, which would be like on our thing starting your program here. Um, but that's just the yeah. Um, yes, Mike, it is completely possible that you could write a program that needs more memory than you have available. It is unlikely, but it totally could happen, right? So this particular computer, 256 bytes of memory, is not a lot, right? Um, one could easily imagine a program that is longer than that, and you would be unable to fit it into the memory here, and there's just no way around that. Um, and with this particular architecture. Now, it's not going to happen for the programs that I have you guys writing, um, but it could theoretically happen, and even to some extent did theoretically happen. So, for example, I think we talked either last time or the time before, I was talking about Pac-Man. The original Pac-Man on the arcade had a more sophisticated architecture than the Atari that you could get for your living room, and that made it a real challenge when Atari wanted to take Pac-Man from the arcade and sell it as a cartridge for your living room. It was hard to do that because they were so limited on memory. So yeah, Mike, that totally, or sorry, Teague, that totally could happen. It will not happen for what I got you guys writing unless, I mean, if you want to go around writing Rube Goldberg kind of code and making it as complicated as possible or unnecessarily complicated for the sake of running out of memory, you could totally do it. But it is possible to do it with to do everything I've asked you guys well within the limitations of this machine. All right, well, it's just after 4 o'clock, so we should probably quit the stream. Um, so I will go ahead and quit the stream, and I will see you guys on Monday, if not sooner, and have a great weekend.